Hi everyone, welcome back to Mark 1 Design EMC channel. Last week we did a practical demonstration showing you as frequency increases, the return path of a RF signal would choose a path that has least loop size, hence least inductance. Some of the viewers suggested, why don't you measure both return paths and give us an idea of that current distribution between the two return paths as frequency changes. I think those are great suggestions. So this week we added this new episode following on last week's episode, and we hope you will like this episode. And in fact, we went a little bit further. After the demonstration, we added another demo which shows you that as frequency approaches to 100 kilohertz or 1 megahertz, really you wanted to use a coaxial cable or shielded cable to achieve your signal integrity for RF signals. Okay, first let's have a look at the test setup. If you missed last week's practical demonstration, please check it out because this week's demonstration really is just a slight improvement compared to last week's setup. As we demonstrated before, we have a signal source and the oscilloscope. Both are battery powered, therefore there is no earthing wire serving as a return path. And we have two return paths really. One is a short, broad connection serving here as a BNC connection here, right? And that is a short connection. And we have a longer, thinner return wire, which is part of this coaxial cable, the black wire. And we monitor both this time, right? So for the shorter path, we have this current probe connected currently to channel 2 of the oscilloscope. And we have this current probe connecting to the black wire, which is the return path of the twisted pair, and that is connected to channel 4. Okay, so the blue trace is the current going through this shorter return path, whereas the green trace is the current going through the other return path. And as always, we also monitor the input voltage in channel 3, so everything's quite clear here. It's worth mentioning that for this demonstration, we keep everything as RMS, right? Simply because it's a lot easier to calculate. So as you can see, currently we have a RMS voltage, roughly 2 volts. And this goes through a 50 ohm resistor as the input impedance of the oscilloscope. So you know, just doing the Ohm's law, we should expect to see something like 40 milliamps as the current going through or going between the signal generator and the oscilloscope. But because the setup we have and the measurements we perform, there is some error here. But roughly, we are only interested in the ratio between return path 1 and return path 2. Okay. So knowing that, if you look at the current frequency, right, we have 1 kilohertz, and what we're going to do is we're going to increase the frequency to 10 kilohertz, 100 kilohertz, and 1 megahertz. And we're going to show you the current distribution between return path 1 and return path 2. And after this, we're going to replace that a black and red wire twisted pair with a coaxial cable, and we're going to do the same. And let's have a look at the difference between the two, okay? So as you can see, right now we are at 1 kilohertz, okay, 1 kilohertz. And the RMS of the voltage is about 2 volts, let's say. But as you can see here, we have some measurement error, perhaps due to all these noise, as you can see, okay? But roughly speaking, let's just record this number here, which is 40 milliamps going through this shorter return path, and about 4 or 5 milliamps going through the long wire, which is the twisted pair wire. Okay, 40 against the 5 at this frequency. So we increase the frequency to 10 kilohertz now, and you can see now here we have reduced the current, which shows at 27 milliamps. Okay, and in this channel, the long black wire return of this. Now we have about 19 milliamps, okay? That's the reading at 1 kilohertz, okay? So moving on to 100 kilohertz. That is 100 kilohertz. So on the shorter path, the current now is reduced to about 20 milliamps, okay? So that's from 40, then 27, now 20, whereas this black wire now is about 21 or 21.5, let's call it 21.5 milliamps, slightly increase, okay? So that is at 100 kilohertz. So we have almost like an equal split, let's say. Now we're gonna increase to 1 megahertz and have a look. 1 megahertz, as you can see, yeah, roughly the same. Again, split up half-half, let's say. So as we know from last week's demonstration, now if you increase to 10 megahertz, 20 megahertz, they will be roughly the same, okay? So you can see that from pretty much 100 kilohertz, the current splits to half-half. 50% of the current use the black wire and 50% of the current uses shorter connection in this case, okay? So as I explained, now we are going to replace this twisted pair with a coaxial cable and see if there's any difference. So I'm going to replace the twisted pair wires with a coaxial cable. But I wanted to introduce the current probe we use because, you know, previous case we used a twisted pair and I can simply clamp a current on the return path, which is the black wire, and monitor the current, okay? And this is about 1 meter long twisted pair. So in order to keep the comparison pretty much similar, I also get a coaxial cable, similar length, slightly shorter. But here's the challenge. How do we measure the current that going through the shield? In fact, as RF current frequency increases, the most of the return current would use the inner shield because of the skin effect. So we need to find a way of measuring the current inside the shield, because if you clamp a current clamp on the outside, according to Ampere's law or Maxwell equation, if you think about it, you will end up zero current because all the field is contained inside the shielded cable. Just to clarify, I'm not measuring the return current in this case, so let's hook it up to the oscilloscope. Alright, so we set it up as a coaxial cable, and really we just wanted to do a very quick comparison. So if you just look at the frequency point, which is 100 kilohertz, okay? So in this case, you can see the current going through this shorter path now is only 6 milliamps. If you remember the ratio we had with twisted pair, clearly you can see that coaxial cable for high frequency signal is a lot better. Let's do 1 megahertz just to have a look. Alright, this is 1 megahertz and have a look. Here, the shorter path is only registered as 1 milliamps, whereas here is about 41 milliamps. Okay, so at 1 megahertz, you can sort of safely conclude that pretty much all the return current will start to use the coaxial cable, whereas this shorter path is being almost like as if it's non-existent. This can also be proved if I remove this now. Okay, so I'm gonna remove this path. Okay, so that is gone, and you can see this current doesn't change. That means really, that current is pretty much negligible. And some of you may also notice that first, remember, when we add current together, sometimes they exceed 40 milliamps, where this, now is pretty much close, right? And also, if you remember, just before this test, at 100 kilohertz, my waveform here, the current and voltage, actually has a phase shift, whereas now it's pretty much in phase. I mean, the polarity is different because this probe has a direction feature. So if I just, for example, connect this current probe the other way around, this would be matching. But if you look at the waveform at 100 kilohertz, you find actually there is a inductive lacking there, right? So all of this is, I'm afraid, is not within the scope of this discussion. It's something I know, but it's going to take us a lot of time to explain the reason. The reason is the current probe we use. You have voltage region and the current region, and when for this particular probe, because of the transfer impedance of the probe, when you operate below 1 megahertz, you are operate in the so-called voltage region. If you want to know the details about this, you can check our RF current probe series. I'm sure you will learn a lot. But really, this test setup is to demonstrate that, when it comes to high frequency, high speed signals, the coaxial cable or shielded cable is a better choice compared with twisted pair. And and also demonstrate how, as frequency increases, current starts to shift from one path to the other. So I hope you really enjoy this follow-up episode, and many thanks for the people who suggest doing more on this subject. So we appreciate it. And I'll see you next week.